Thank you. So I think that my volume of voice is enough to reach all of you, so I don't need a microphone. So, okay, my name is Pasquale Orgiani. I'm the scientist in charge of PLD here in Trieste. And today I will talk about the possibility of grow perovskite in film and heterostructure by pulsed laser deposition. Not only perovskite, but this will be an introduction to the PLD. And then if there is time and you are not so hungry, I can also show some not oxide thin film. First, we spent the morning talk about thin film. So first of all, why we are interested in thin film? As I keep on repeating to everybody, is not to compete with people growing single crystals. So when you want to investigate a specific material, you are so lucky to have a crystal, just go for the crystal. It's way more nice under a structural point of view and so on and so forth. But when you need the thin film approach, so first of all, you need a thin film when you want to explore very thin regime, basically one single layer, one atomic layer of any material. This cannot be done by crystals. They just simply will break. When you want to modify the film, so film usually are grown on substrate, then you can apply a strain to the film, so you can stretch a little bit, you can compress a little bit your film, and then maybe this can alter or modify the electronic properties of the film. Another reason is that sometimes there are some some structural phase, which are not thermodynamically favorable in terms of single crystal. So basically you cannot have it as a crystal. On the contrary here, since you are using a substrate, you can somehow bend a little bit the rule of thermodynamics, and then you can get some not stable or not so stable phase. Of course, one possibility is that since you are growing a film on a crystal, you can change the orientation of the crystal, and then you are changing the orientation of your film. This is particularly important when you have anisotropic properties in your material. And last but not least, the most important part is that with thin film approach, you can grow heterostructure, more or less like your sandwich at home. So you can combine different material, not necessarily a small number. You can even design a very complex material. And of course, this cannot be done by crystal. In particular, about one class of material that has been so successfully grown by PLD is the oxide perovskite. So perovskite is generally known as a formula AbO3 in a cubic arrangement. At the B site, usually you have a transitional metal, and in S site you have some alkali earth or rare earth elements. So what is interesting in this class of material is that you change the B element, for instance, from copper to manganese to ruthenium, whatever, and you are changing the physics of the system. So you can have ferroelectric material, you have conducting material, you have superconducting material or magnetic material, just simply changing the B element. The A element actually is not meant to drive the physics of your system, it's just meant to provide the charge. For instance, if you replace a trivalent element with a divalent element, you are doping your system with holes. Or if you are changing a trivalent with a tetravalent, you are doping your system with electrons. And as a side effect, you can also apply an internal stress. By changing the ionic radio of the central atom, you are applying a stress. Why is it so important with the perovskite, this way of controlling this structural deformation? Because in most of the case, the physics of the perovskite is driven by 3D orbitals, which are known to be highly anisotropic. This means that you change a little bit the distance, you change a little bit the angle between the material, and then you are changing the overlap of the orbitals in a very, very strong way. Then you can turn to be an insulating to a metal guy, just simply changing this small angle at this small arrangement. Okay? Why are so interesting this class of material is because by changing the structure you can have all this kind of material, but more important, you can pile up one on top of each other. This is because perovskite has, as I said before, more or less the same structural arrangement. So nearly they are all of them cubic, and they have a very very good chemical stability. It means that there is a very small interdiffusion between each other. So you can have a very flat, very precise, very sharp interface between them. So not only you can combine a different, they used to call it functionalities between the material, but especially in the last year, there are new phenomena arising at interfaces between these two materials. There's some interface phenomena which has nothing to deal with the constituent of the material. So it's very well known, probably if you are at a conference, you have heard about this LAO-STO superconducting interface. So basically, both LAO, lanthanum aluminate, and something titanate are insulating material, but if you face one to each other, at interface, you have a two-dimensional electron gas, so you have a metal, which even became superconducting at a very low temperature. But you are starting from two insulating material. So this is a sketch to see how many materials you have in the perovskite family, and here how many substrates you have in the perovskite family. So you want to stretch your sample, like for instance, we are growing, let's say, YBCO. You want to compress your system, then you grow on this kind of crystal. You want to expand in the plane your system, then you grow on this substrate, and so on and so forth. But of course, PLD is not the only thin film deposition technique. So this morning you have heard about MBE, but you can also grow thin film by sputtering, or in which basically you have ions that bombard the target, and then this element just collapse onto the substrate. Or you have some chemical vapor deposition technique. Basically, you have a precursor that provide you element, and at the substrate, at the surface of your substrate, there is some chemical reaction. So, but just not because I'm talking about PLD, there are some advantages and disadvantages with all kind of technique. So I will try to give you the flavor of what can be the advantages of using PLD, and what also what are the backdrops, drawbacks in using PLD. So what is the principle of PLD? The principle is very simple. So you have a laser beam, a pulsed laser beam, very intense, short. I will not say so short because we are talking about 10, 15 nanoseconds, but very intense, that are hitting a target. What is the target? I will tell you later. But the target is just powders or crystals or whatever you have in mind to want to deposit it on your film. This intense but short pulse cannot dissipate energy through heating of the substrate, and what happens, you just destroy all the chemical bonds of the element of the target. These are ejected far from the from the target to the substrate, and then you have the deposition. This is a typical picture of the plume, meaning there is a laser coming here, hitting a target, and here there is this expulsion of material that are flying in this direction. Here there is the crystal. You can find plenty of pictures of PLD apparatus. What is the advantage of PLD? So first of all, you can have plenty of target. Means that for each material you want to deposit, you can have your target. So STO, LAO, YBCO, whatever. Can be very simple, like here in Trieste, we have 4 target, so we can combine 4 different elements. Can be a little bit more complex with the 6, and we will soon have this. And it can be even more complicated to have 10 of them. So basically, what happens is that you have your laser position fixed, and then just you move a carousel with a lot of target on the laser path. So this is why it's an ideal technique to grow heterostructures. This is a school, so I will try to be as fast as possible on formula to not bother anybody. But basically, this is after 24 pages of a paper, you can find that the volume that is ablated is somehow related to this equation to reflectivity of your target. The more is reflective, the less you are ablating. It's depending of the energy of the laser pulse, and more or less is related to the capability of your target to dissipate energy through heat. As I said before, you have an intense laser pulse arriving. If it is not able to dissipate through heat this energy, then you have the ablation. So this is just to give you an idea that the less conductive and thermally good is your target, the better is the ablation. So that's why the PLD works so nice with insulating material, even better with crystals. This is a classical scheme. So there is a threshold. Above that, you have the ablation. Below that, you don't have the ablation. And this is the classical laser pulse in energy with some threshold. So this is the basic idea of what is the ablation for the PLD. What are the lasers used for PLD? Not very fancy laser, just need to be very intense. And for a lot of years, just recently they use a different kind of laser, but in 95% of the case in a PLD lab, you will find an Excimer lasers that now in very old-fashioned style would be orange. Now you will find the same kind of laser, but it's gray just because the coherent bought the lambda physics. But basically 95% of the people use the same laser. It's more than 20 years. This is a classical spot. I don't know how many of you are familiar with laser. Excimer is very, I would say, very simple kind of laser. You have two gas, krypton and fluorine. In ordinary, so in a steady state, at the beginning they are just separated. So krypton is on its own, fluorine is, they don't talk to each other. But you have some discharge, and then you ionize the krypton, so the noble gas. It can be combined for a very short time with the fluorine. Of course, it's a metastable state, so it will soon collapse, and then will emit radiation. So why the people has used Excimer lasers in PLD? Because this kind of laser is very efficient. You don't have an active element which can somehow drag away photons. Because when you have this emittance of photons in UV, you don't have the dimer. So the dimer cannot longer exist. So it cannot absorb back some photons. So they are very, very powerful. Very recently, the people start to use also neodymium YAG, which is in infrared. So it's not in UV, but it's in infrared. But as I was saying before, most of the people use PLD. Why? Well, mostly because it depends on the uniformity of the laser spot. This is classical image, in which you can see that over a very large region, so we are talking about a centimeter, the intensity of the laser spot is very good. Why it's so important that your laser profile in energy is very uniform? Because I told you half of the story. I told you that here you have ablation threshold, and then you have the ablation process. But what happened here? When you are close the ablation process, which basically is when you have this huge spread of energy in your laser pulse. What happened? It happens that most of the laser pulse is used to good at ablation. Part of it is used to do a less efficient ablation. Let's try to understand what happened. You have your pulse that is definitely above the ablation threshold. What do you get? You got a thin film, so you are able to ablate your film. Here, you are far from the ablation threshold. What you have? Nothing. You are not able to ablate your film. What if you are here? You have a mix. I told you that if you have enough energy, you destroy any single chemical bond of any element of the target. Of course, you have a little less energy. You are not ablating a single element, but you are ablating clusters. Huge drop of element, which are seen here. And this is not what you need. You want a single film without droplets. So one important parameter of PLD is the uniformity of your laser. This can be achieved, even improved, by using some iris in the PLD. Here is shown that, for instance, this is a very complex material like lanthanum, barium, manganese, oxygen 3. And you can see when you reduce the energy, you start to have droplets, and even you have less amount of some element. Second point, this is a long-standing discussion where to put your laser beam, not in the focal point. because focal point will modify your laser energy profile, and this again will turn you in this situation. So the most important thing is to put your target in image point to have a very uniform and flat, from the energy point of view, energy pulse. Second huge difference between PLD and the other deposition technique. The elements are provided by an ablation process, meaning they are accelerating quite a lot from the target to the substrate. This means that this element are able to reach the substrate even if the background pressure is not so low. In MB, you cannot deposit it above 10 to -4 because the elements are literally gently fly towards your substrate. If you have too much gas on the side, they will draw your element away from the substrate. Here, in PLD, they are accelerating, they are fast, meaning that they stop at several millibar. So you need 2-3 millibar to stop completely this flying element so they cannot reach your substrate. And this is one of the major reasons of the success of PLD. This is because if you can increase the background pressure, for instance, with oxide, in which oxygen is a very volatile element, this means that you can grow at several millibar, meaning that in 1987, soon after the discovery of YBCO, that is a superconducting material based on oxide, they were able to provide as grown YBCO film, superconducting film, without doing any post-annealing process. So they already got all the necessary oxygen. Of course, here you see this effect of the background pressure. Here you have a free expansion of the gas. You have light everywhere. And here you see this plume more and more confined. This is one important thing of PLD. So you have to also think the interaction of your plume, which is this amount of material they are flying, with the background pressure. So this is a classical CCD experiment. Basically, you have a camera here. So you have a camera on the pulse path, and then you are acquiring the position and the shape of this pulse coming in time. So when you have a very low pressure, you see these species. They are basically flying towards the substrate. When you increase the pressure, you see that this plume is always more confined. What is happening there is basically happening that the background pressure is keep all your bunch of elements close to each other. They are arriving all together. Of course, what happens when you increase too much the pressure at a certain time, at a certain level, will completely stop your flying element. And this is what happened here. This is the front position. You see that at 1 millibar, everything will stop at about 2 centimeters from the target. But it's still okay. It's enough that your crystal is 2 centimeters away or a little bit less. If you put your target at 2 millibar at let's say 5 centimeters, you will not have deposition. So this is another tool that you have to control in PLD with respect to other thin film technology. Of course, this can be, the situation is even more complicated than this, because in your plume you could have light and heavy element at the same time. And of course, this capability of thermalize element depends on the mass of the flying object. So what happened here is that big element like lanthanum or barium can be easily stopped by the plume before arriving. So what you could have in your film is that you start from some stoichiometry in your target, and you have your film with some deficiency of one of other element. This is because they are interacting with background pressure. But not the story are all bad, meaning that if you are usually below 10 to -2, you are in so-called free expansion of the plume, meaning that you don't have this kind of problem of stoichiometry. But this is something that you should control in your experiment. Last point is that, and this is something that is peculiar of PLD, is that since these elements are so fast are so traveling so fast that they are bumped with background pressure, they can be ionized themselves. So in this case, you can have lanthanus plus, barium plus, manganese plus, and whatsoever. What is the importance of this step with respect to the other technique? That sometimes having ionized element flying on your substrate is better because they are more reactive. So they can easily react with the other element. This is not so true for oxide, but it's extremely true for another compound grouped by PLD, like magnesium diboride, in which they discovered that if they have boron in some ionized state, the growth proceed in a better way. So, third time, you see this image. Even in PLD, you can use read to monitor your growth. This is a classical read with the specular spot going up and down, and then there is this mirror no mirror surface, or in this Dirichlet method that Sasha just mentioned before, you are not evaporating, you are not tracking this reflected beam, but the diffracted beam. What is particular of PLD with respect to the MB is that I told you before that you can grow in PLD up to several millibars of oxygen. There's no way that you can use an electron gun with several mil of oxygen outside. The people just invent what is high pressure, near ambient pressure reed. Basically, it's the same reed gun that you have seen, but it's a huge can here. So the electrons are provided very, very close to the substrate. So basically, you can use this kind of reed at 1 millibar. So you can follow the growth also to this very high pressure. And it's just because you have this differential pumping here. So nothing different from fundamental point of view, just technical. Okay, now we finished this introduction on PLD. And so you see, okay, all this headache have some good news. Yes, fortunately, there is some good news. And the good news is that you can grow a very large variety of sample. I would say you have definitely more flexibility with PLD than any other system, because in PLD what you are doing is ablating a target of a material. You change the target, you change the material. This means that, for instance, in a PLD, at the same time, I could have a one oxide and one not oxide material. Probably they will kill you. On the contrary, here, the elements are provided by ablation. So you change the target, you change the material. What we have done in Trieste is to put a PLD system directly connected to a beamline of the synchrotron, in which you can do many of things like RPS, spin RPS, surface, learner science, and XPS. Why so important to have a PLD directly attached to a synchrotron beamline? Because most of these techniques are very sensitive to the surface. So what the people have done up to now, they just have your sample at home. So they go back here, they come back, they come to the beamline, they have this carbon on surface, they have some bad surface, some contaminant. So they heated up the surface, they even do some spattering of the surface to remove carbon, and they try to measure the sample. Try to do this with oxide. You heated up your sample, you could lose oxygen. You spatter your surface, you are ruining your surface. So if you have flat surface, then you have something else. You have a system in which you have a heterostructure. Let's say 2 layers of one material, 1 layer another material. You cannot do the spattering. You will mix up everything. So what is the strategy? The only strategy is that you grow your field exactly in the same place where the other techniques are available, and then you transfer in situ, so don't touching the surface, the system. So this is a sketch of our PLD, and basically this is the heater, this is the carousel, this is the sample holder on top of which there is a crystal. I don't know if you look at them. And this is the so-called arm of the UFO. It's the arm that take the sample and transfer the sample in situ to the other experimental chamber. Here I just reported the oxide thin film, but there are way larger variety of elements that you can deposit by thin film. And here, what I was saying before, it doesn't really matter the form that you have the target. It can be either a crystal, it can be powders, it can be pellets. You don't even need that your target is the same crystallographic phase of the material that you want to grow. You just need the elements. And this is the great advantage. So what do we do here in Trieste? We investigate what are the surface state of a large variety element, in particular of oxide. Here there are few elements like topological insulator or STO or titanium dioxide. And just to give you an idea of what you can do, today I will talk about titanium dioxide. So we just finished the tutorial part of PLD, then let's see what we can do with PLD. Brief motivation, why we are interested in titanium dioxide. Probably is one of the most investigated compound in the world. You can use for almost infinite number of applications, like this very fancy, like you cover your car or your glass with titanium dioxide and it will be always clean. There is a Nissan project that paint your car with this kind of titanium dioxide. Can be used like in catalysis and so on and so forth. What is the main problem? That the anatase and the rutile has a gap in their band of about, I remember, in UV. So this means that this material, to absorb light, this light has to be in UV, which is available in the lab, is not so available outside. So the fraction of UV in the light in ordinary light is very small. But the people discovered if that you create in some way this defect state, basically introducing some defect in your system, they can also absorb it in the visible light. So about this technological point of view, the people also discovered that at the surface of titanium dioxide, you have the appearance of two-dimensional electron gas. So you have a very narrow two-dimensional, 2D, electron gas just at the surface of your titanium dioxide. This has been shown in the past, like in 2013, first by Moser and co-author, and then is exactly what we want to investigate. First of all, we want to see how we can modify, investigate this two-dimensional electron gas, and what is the nature of this two-dimensional electron gas. If it's related to the vacancies that we are creating in the sample, if it's depending on something else. So with this in mind, we of course grow thin film because we want to do anything, all this kind of advanced characterization after. So of course, since we are dealing with thin film, as a first step, of course, we just select one substrate which is supposed to not induce any strain in your material. So basically, titanium dioxide has the same in-plane lattice coordination of lanthanum aluminate. So you can grow film. I don't know how many of you knows this reciprocal space map measurement. Basically means that in plane they have the same lattice parameter. So titanium dioxide just match the lanthanum aluminate in-plane coordination. Of course, you investigated this by X-ray diffraction, if you see if they have these nice fringes, and even more sophisticated analysis like TEM, and then you see that the film is flat. Very nice. But what we want to do with this very nice film, we want to do all these kind of characteristics. So first, we investigated the surface. They are flat, but also TM was saying they are flat. But we start to see that at the surface, when they are still inside the chamber, they show a reconstruction. And it's a very particular reconstruction because in other material, a reconstruction is something that is due to oxygen deficiency. So you change the oxygen content in your film, and then you see a different surface reconstruction. In titanium dioxide, it doesn't matter what kind of oxygen we are using during the grow, meaning no matter how many oxygen is in your film, the surface is always the same reconstruction. This is supporting a scenario in which actually the reconstruction is due to the fact that every four atom of titanium, some of them are jumping out. This is because of polarization of the surface. So it does, so it's so complicated, but this surface reconstruction is due to the fact that in vacuum, what happens is that the surface has this titanium element, which is supposed to be this gray, jump out of your film. As I said before, you can take your sample and characterize your sample. The two main techniques that we use at the synchrotron are X-ray photoemission spectroscopy and X-ray absorption spectroscopy. So the first one, very briefly, because I think that you will have a lecture on Thursday or on Wednesday about synchrotron technique, but just to give you an idea, photoemission basically is that you have X-ray photons that just bump some electrons, core electrons out from your material. So this means that since these energetic levels are characteristic of the element, so they change from element to element, you have a chemical map of your element, so of your material. Now here there is just titanium. Plus, if you have a different oxidation state, so titanium can be either in 2+, 3+, or 4+ state, this binding energy slightly is different among the different valence states. So you can not only have a map of the element that you have in your material, but you can also have a map of the valence state of your material. Why it's so important? Because we are in titanium dioxide tuning the oxygen content. Basically, we are trying to reduce it. If you reduce oxygen, which has an electronegative charge, you expect that some titanium goes from a 4+ state to a 3+ state because there is less oxygen. So there's no need to be in a 4+ state. So nature always loves to be square on electrical point of view. And the second technique is X-ray absorption spectroscopy, which basically is a process, a resonant process, which puts some of the electrons on the core level from the empty state. Why this technique is so important for thin film? Because they provide information about the empty state. Empty state depends how the material is organized. So if it's a cubic, there is some empty state. If there is some strange arrangement, there are some other empty state. So depending on what is the shape of this absorption spectra is changing depending on the material that you are growing. Too much complicated about that, but what is the last result of this is that you can tune titanium 3+, which is important for catalysis, remember? You can tune titanium 3+ by oxygen pressure. So outside you change oxygen in the background, and then you change the amount of titanium 3+. In a not too trivial way, unfortunately, so just not simply that you remove oxygen, you increase titanium 3+, but it can be done. So, but what about the surface state? So this is the bulk. So it's in the film. But what is the surface, the situation of the surface? To do that, we use ARPES, which stands for angular resolve photoemission spectroscopy, which has this advantage to be very sensitive to the final layer of material. So it's perfect to investigate the surface state. We reproduce the same result of Moser, and as a matter of fact, on untreated sample, you see about the band structure, you see some 2-DEG, meaning that is metallic, this is a Fermi, 2-DEG at the surface of your film. Very complicated, you can map this surface state in different brilliant point of the brilliant zone, but what's interesting is that this two-dimensional electron gas is very, very similar to two-dimensional electron gas found in another oxide thin film, like in STO. So basically there are these two parabolars, so this is STO, this is titanium dioxide. So basically it means that even though the material below the surface is changing, the surface is practically behaving the same way. Or I would say not exactly the same way. But what is new about the titanium dioxide with respect to the STO? The new part is that there is a very practical way to perform an experiment of a wave in a box, meaning that you have a two-dimensional electron gas at the surface, and then you have some atoms going up any 4 titanium ions. This act exactly, they play the role exactly like a box, a boundary condition. So what you expect for the two-dimensional electron gas, that he field is modulation. So this is exactly what the people has measured, and also us. So you have this two-dimensional electron gas that in K space is reproduced by some replica, which basically are these confinement that are created by this edge. Of course, you change the in-square orientation, then you can twist these flowers in all the direction. Let's make this conclusion. I hope to show you that the PLD is extremely flexible technique. Of course, you have problem that unlike the other technique, you have the interaction of the plume with the background pressure, which has always to be taken into account when you are growing your film, but still allow you to grow in a very different background pressure, up to 1 millibar, 2 millibar, 3 millibar. Okay? Then you can apply any kind of monitoring system like a read, also for PLD. And of course, this technique is still having a lot of success with oxide-electron film. This is because oxygen is extremely volatile, and PLD, since you can grow at very high pressure, then you can put a lot of oxygen in your film. Of course, you can avoid this surface contamination by transferring in situ the target. And this is another good reason to have a PLD on a synchrotron beamline, because it's very flexible. So every week, not every week, every month change the users, so change the material, and then we can be very flexible. So this is one example of tailoring properties of material by using thin film. So more or less this is the same, and I prefer to answer your question than to show another example. Okay? Thanks.